Welcome to a brief introduction of the DS jet mixing system, and an overview of how it can revolutionize the way tank owners think about sludge and tank cleaning. For as long as transporters and refiners have been storing crude and other heavy oils in large above-ground storage tanks, they've had to deal with accumulated tank bottoms, sediment, and water, what we commonly refer to as sludge. Conventional methods of preventing sludge buildup were attempted through agitation of the product inside the tank, moving it continuously throughout the tank. This was generally accomplished by the use of side-entry propeller mixers. But side-entry props have some significant limitations. Firstly, their general mechanical design, that of a shaft spinning at a high rate of speed through a bushing and turning the propeller. This design tends to result in leaking around the packing to the outside of the tank. This happens so frequently, in fact, that many tank operators don't run the mixers continuously, as they were designed to do, for fear of developing leaks. Secondly, side-entry propeller mixers don't generate enough fluid velocity throughout the tank to keep the heavier wax molecules from falling out of suspension and starting the process by which sludge is formed. This can be noted by the very typical profile of accumulated tank bottoms found in storage tanks with SEP mixers installed. As is often seen, the area in front of the mixer is generally free of sludge. However, beyond the effective radius of the propeller blades, the sludge is not only formed, but is piled up to levels such that the floating roof of the tank often can't be landed, resulting in operational issues and lost inventory. In an effort to solve this problem, a number of designs that incorporated jet mixing, the introduction of a fluid jet into the tank, were introduced to the marketplace. These generally used a stream of product taken from the tank itself or from another source, moving it through a large pump and injecting it back into the tank using a jet nozzle. The most notable of these new jet mixers was the P43, developed by Exxon in the early 1970s. Though a huge improvement over propeller systems, certain engineering flaws, the double right angle offset that diminishes fluid flow by as much as 50%, for example, caused the solution to be less than optimal. In order to understand why jet mixing can be effective, it's helpful to understand what creates sludge in the first place. In most cases of crude oil sludge accumulation, the bottoms, or sludge, are paraffin-based. This means that the primary constituents of the sludge are long straight-chain hydrocarbon molecules, or paraffins. In the majority of sludge, as typically seen, even the very bad sludge, the paraffin content is at least 80%. Usually the other components are inorganics, asphaltenes, and water. There's very little in the way of a body of academic work or research with respect to sludge formation. However, it is possible to draw some correlation from the study of sedimentation. Research by a number of sedimentologists, namely Hjulstrom, Sundborg, and Shields, has qualitatively and quantitatively equated fluid velocity with the ability of that fluid to maintain particles in suspension. We've always kind of known this intuitively as it relates to crude oil, hence the introduction of propeller-type mixers to attempt to keep the product in the tank moving. The critical velocity of a typical crude oil required to keep sheared paraffins in suspension is between 3 feet and 5 feet per second. For instance, if crude oil is traveling down a pipeline at 3 feet per second or greater, it's very difficult for paraffins to consolidate and form wax inside the line. However, should the speed of the fluid drop significantly, it becomes much easier for wax to form. This is the same phenomenon that causes sludge formation in the bottom of storage tanks. When the crude or parent crude enters the storage tank, it is more or less homogeneous, as a result of the mixing experiences during transportation. Therefore, mixed evenly throughout the crude are all of the constituent molecules, including the long straight-chain paraffins. With time, and in the absence of sufficient fluid velocity, these long straight-chain paraffins will attract to each other, or flocculate. Eventually, a number of paraffins will combine to form a particle that is more concentrated and dense than the surrounding oil. As a result of the differences in density between the aggregated particles and the surrounding oil, these particles slowly make their way to the bottom of the tank, under the influence of gravity. Initially, these particles are disorganized and stacked randomly on the bottom of the tank, forming what could commonly be referred to as a gel. Over time, especially in the presence of changes in temperature and changes in hydrostatic pressure, the gel will further organize itself and stratify, forming a more cohesive, viscous sludge. Paraffin-based sludge is thixotropic, non-Newtonian, meaning it will thin or become less viscous when subject to shearing forces. The most effective way to introduce shearing force into a non-Newtonian fluid is through a submerged high-velocity fluid jet. And that is specifically what the DS jet mixing system is designed to do. Like early-stage conventional jet mixers, it utilizes a fluid jet. But its patented inline design enables the fluid to maintain a discharge pressure of approximately 150 pounds per square inch. Due to its unique design, the DS jet mixer can be activated and operated without taking the tank out of service or lowering the product level. This brief video will show us how. The DS jet mixer sits resident on the storage tank in its dormant configuration. When the time comes to activate the unit, the API conformant cover is removed, the secondary and main ball plugs are removed, and the expandable plug in the neck of the mixer remains to seal the unit and isolate the product in the tank. The stinger is then screwed into the gimbal, and a 4-inch full port ball valve is attached. A stuffing box is bolted to the ball valve, and the retraction tool is inserted to engage the expandable plug. The plug is unscrewed and pulled back through the stinger and ball valve. The valve is closed, and the retraction tool, plug, and stuffing box are removed. The DS jet mixer is now ready for hookup to the pump for jetting. The DS jet mixer is designed to rotate about 120 degrees in the horizontal plane. This is accomplished by allowing the gimbal to float on 2 pins and between 2 O-ring seals. As the unit crosses the tank, the paraffins are gradually dissolved and resuspended into the parent crude. When the activation has been completed, the process is reversed and the DS jet mixer is placed back in dormant configuration, awaiting its next activation. The pumps used to power the DS jet mixing system are the AOS 450 and AOS 550, specifically designed solid handling pumps that produce volumes upwards of 2,500 US gallons per minute. In addition to results from the more than 275 installations around the world, we employ advanced computational fluid dynamics modeling software, or CFD systems, to ascertain the performance of the DS jet mixing system and the fluid velocities obtained. This model shows the performance of the DS jet mixer over a period of 24 hours with an initial 12-hour sweep across the entire floor, and a static mix in the extreme left position lasting 12 hours. We can see that the jet generates fluid velocities ranging from 24 feet per second to 10 feet per second, immediately surrounding the jet wall. You'll recall that the velocity required to maintain wax particles in suspension is 3 to 5 feet per second. The velocity required to shear the wax into longer straight-chain paraffin molecules is actually much higher, at 6 to 8 feet per second. The higher velocities generated by the DS jet mixer, however, transfer enough kinetic energy to loosen and suspend heavy sludge that may exist closer to the tank floor. On tanks larger than 150 feet in diameter, multiple DS jet mixers are installed and activated simultaneously, as shown in the model here. You will note that as the mixers are moved through 120 degrees of horizontal motion, the entire area of the tank floor is subjected to the required fluid velocity to resuspend accumulated sludge and shear the wax molecules back into long-chain hydrocarbons. Let's look at some before and afters that demonstrate the types of results we've seen. Real-world results over the past 10 years speak for themselves. Numerous cases, some shown here, have proven that the DS jet mixing system can reduce accumulated tank bottoms by up to 99%, often resulting in significant profits for our customers in reclaimed usable hydrocarbon. In the case of this tank, over 10,000 barrels of product were reclaimed, with a recovered value of nearly $800,000. This particularly difficult project began with almost 33,000 barrels of sludge in the tank. Over a period of time, and by shipping multiple batches in order to keep the product on spec, the DS jet mixing system recovered over 28,000 barrels of usable product, well over $2 million worth. This project was executed in February when the sludge in the bottom of the tank was exceptionally cold and firm. Ultimately, the DS jet mixing system resulted in an 85% reduction in waste. Cost and the benefits of recovery are one element, certainly, but use of the DS jet mixing system also makes compliance with regulatory guidelines easier. Take API 2016. Section 6.1 states, employers, owners, operators, and contractors shall establish and implement non-invasive procedures to remove as much heavy product, sludge, and residue as possible from the tank before the tank cleaning workers arrive. This minimizes atmospheric emissions and reduces the potential for flammable and toxic exposure hazards associated with removal when opening and entering the tank. It goes on to say in section 6.1.4, employers, owners, operators, and contractors should reclaim and recycle as much recoverable product and usable components of the sludge and residue as possible in order to minimize the amount of hazardous waste. So API is pretty clear about what it would like to see in that regard. Ideally, a method or process of reducing the amount of sludge in a tank and reclaiming as much hydrocarbon as possible, thereby reducing or eliminating the amount of waste generated from the final cleaning operation, and also reducing the tank outage time. Both would fit the bill with respect to what API recommends and what the tank owners and operators want in terms of cleaning operations. We've already talked a bit about some of the benefits to this approach. More recovered product, less tank downtime, more usable tank volume, less risk to workers, and of course longer tank lives that result from regular removal of corrosive elements. The DS jet mixing system helps tank owners and operators accomplish all of this in a manner which can recover the initial investment with its first use. We believe that new ideas and better solutions exist that can help our customers confront their operational challenges head-on. The DS jet mixing system is key to our innovative tank bottoms management system.